Okay, lesson 20 on the Laplace transform. That remind you, we have a makeup class this Friday morning at 11. And let's see. So we've been talking about, and we're going to continue to talk about the Laplace transform. I sent out some homework for Friday on the Laplace transform. And I'm going to go over parts of it actually right now, because the important thing is to see how to solve ordinary and partial differential equations using the Laplace transform. Are there any questions to start off with? So let's recall the Laplace transform of a function f of t is given by the integral from 0 to infinity, f of t e to the minus st dt. This is an improper integral because we're going from 0 to infinity. There's a parameter s, which makes this a function of s. And we sometimes write this as capital F of s if the function is little f. And we also sometimes write this as L of f evaluated at s. So these are alternate notations. We use both of them. And the integral certainly converges if f of t is less than some constant times e to the ct for some from some point on, and if it's continuous or piecewise continuous and so forth. But so long as the function f of t in absolute value doesn't grow any faster than an exponential function, then this integral converges. And that's just as an exercise. Let's calculate the Laplace transform of the sine function. So example, suppose we let f of t be the sine of t. So the Laplace transform of the sine of t is the integral from 0 to infinity sine t e to the minus ts dt. And you have to know how to calculate this. So this was an exercise usually in freshman calculus. It involves doing two integration by parts. Turns out to be equal to this. I think I might even have done this already in class, so I don't want to do it again. It's equal to that. Some people prefer to write this as s squared plus 1. And slightly more generally, if you take the Laplace transform of the sine of at, that's equal to a squared over s squared plus a squared. So this is this is the case a equal 1. Let me do a very easy example. Suppose we take the function f of t identically equal to 1. Then the Laplace transform of this is what? It's the integral from 0 to infinity 1 times e to the minus st dt. This is the limit as b goes to infinity, the integral from 0 to b e to the minus st dt. We know the antiderivative of e to the minus st is minus 1 over s e to the minus st And we evaluate that from 0 to b and take the limit as b goes to infinity. So that's the limit as b goes to infinity of minus 1 over s e to the minus sb minus 1 over s times e to the 0 makes this plus 1 over s. And as b goes to infinity, if s is positive, this goes to 0. This equals 1 over s. So if we take the constant function f of t equal 1, the Laplace transform of 1 is 1 over s. Now, you notice that when you're taking the Laplace transform, right, this is the definition. It doesn't matter what values f of t takes on for t negative, you're only integrating from 0 to infinity. So if two functions are different but agree from 0 to infinity, then their Laplace transforms are the same. So here's a very simple example of that. There's a function in mathematics called the Heavicide function, h of t, which is the simplest step function. This is equal to 1 if t is greater than or equal to 0, and 0 if t is less than 0. So this is the function which looks like this. For t negative, it's 0, and then for t non-negative, it's 1. It's this step function. And what is the Laplace transform of h of t? Well, it's also 1 over s. Why is that? Because from 0 to infinity, this function and the constant function 1 look the same. So they have the same Laplace transforms. An interesting thing about the Laplace transform, about the Heavicide function, is for a greater than 0, h of t minus a is what? Well, when you replace t by t minus a, you learned in Calc 1, this shifts the graph of the function a units to the right. So this function is 0 when t minus a is less than 0 or t is less than a, and it's equal to 1 for t greater than a. So this is the step function, but it steps up at a. Suppose I wanted to take the Laplace transform of the function h of t minus a. That would be the integral from 0 to infinity h of t minus a e to the minus st dt. But this function is 0 until you get to a, and it's 1 starting at a. So this is really the same as the integral from a to infinity, e to the minus st dt. What is this integral? Let's see. Let me try to avoid calculating it by being a little bit clever. This is the integral from a to infinity, e to the minus s t minus a times e to the minus sa dt, right? Because this is minus st plus sa minus sa. I can take this outside. E to the minus sa, the integral from a to infinity, e to the minus s t minus a dt. If I change variables, if I let u equal t minus a, this is e to the minus a, the integral from 0 to infinity, e to the minus st dt. And this integral we already saw is 1 over s, so e to the minus sa over s. So this is the Laplace transform of the shifted Heavicide function. Now, when we solve differential equations using the Laplace transform, we take the Laplace transform of the equation, we get some sort of polynomial usually, where the unknown is the Laplace transform of the solution. When we solve that, we found the Laplace transform of the solution, and then we need to do the inverse operation. We have to go back and find the function whose inverse, whose Laplace transform is what we're looking at. And for that, we use tables of Laplace transforms and inverse Laplace transforms. For us, everything we need is in that little table on page 114 of Logan's book. And for example, you will see there that the Laplace transform of h of t minus a is in fact this, 1 over s e to the minus sa. So if you ever end up with a function whose solution has this as its Laplace transform, then you know the function is this step function, the shifted Heavicide function. Okay. Any questions about this? One of the beautiful properties of the Laplace transform is that if you have a function little u, and say u of s is the Laplace transform of u of t, and v of s is the Laplace transform of some function v of t. If you multiply the Laplace transforms, that's not the Laplace transform of the product of the two functions, but it is the Laplace transform of the convolution of the functions, where the convolution of two functions, u times v of t, this is the integral from 0 to t. I'm going to use x as a variable because I like x. It's easier for me. U of t minus x, v of x, dx. This is the definition of the convolution of two functions. And it's important to be able to compute the convolution. Let me do a couple of examples. So couple of examples. Suppose we take u of t equal to t, and v of t equal t to the fourth. So u star v of t is the integral from 0 to t, u of t minus x, v of x dx. That's the integral from 0 to t, u of t minus x is t minus x, v of x is x to the fourth dx. That's the integral of 0 to t, tx to the fourth minus x to the fifth dx. So I can write this as two integrals. It's the integral from 0 to t. T I can take outside. X to the fourth dx minus the integral from 0 to t, x to the fifth dx. This is t times, this is 1/5 x to the fifth. And when you evaluate that from 0 to t, you get 1/5 t to the fifth. And this is 1/6 t to the sixth. So this is t to the 6 over 5 minus t to the 6 over 6. And 1/5 minus 1/6 is 1 over 30. So t convoluted with t to the fourth is 1/30 t to the sixth. Okay. Okay. What are the two important properties that connect Laplace transforms and derivatives? So let's start with a function of one variable, f of t. Suppose I want to take the Laplace transform of f prime of t. That's the integral from 0 to infinity, f prime of t, e to the minus st dt. When you integrate by parts, I write f prime of t and e to the minus st. The antiderivative is f of t, and the derivative is minus s, e to the minus st. So this is f of t, e to the minus st from 0 to infinity, minus the integral this way. Minus times minus makes this plus s, f of t, e to the minus st. This is just the Laplace derivative, Laplace transform of f. This is equal to f, capital F of s. F of t, e to the minus st, as t goes to infinity, this goes to 0. So you just get minus what this is when t equals 0, which is minus f of 0. So the Laplace transform of df dt is s times the Laplace transform of f minus the value of the function at 0. If we want to find the Laplace transform of the second derivative, well, of course, the second derivative is just the derivative of the first derivative. So for this function, this is s times the Laplace transform of df dt minus df dt evaluated at 0. And this The Laplace transform of df dt is f of s minus f of 0 minus f prime of 0. So what we get is s squared f of s minus f of sf of 0 minus f prime of 0. And we could keep going. If we wanted the third derivative, if we take the third derivative of f and take its Laplace transform, this is the Laplace transform of the derivative of the second derivative. So this is the Laplace transform of the derivative of oops, put it better. So this is s times the Laplace transform of the second derivative minus the second derivative evaluated at 0. And the Laplace transform of the second derivative is this. If you multiply this by s, you get s cubed f of s minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. And it should be easy to figure out how to get a general formula for the Laplace transform of the nth derivative of f with respect to t. You would expect this to be s to the n f of s and other terms which simply generalize this. So, but we're not going to consider any differential equations of order greater than 2. So for us, the two important formulas are this for the first derivative and that for the second derivative. All right. Any questions about this? So let's try to solve a differential equation. Okay, we need a differential equation. Suppose I take one that looks like pretty simple. So here's the following ordinary differential equation. U prime plus, I don't know, 10u equals 0 with the initial condition that u of 0 is minus 7. And we want to solve using the Laplace transform. So let u of t be a solution, if there is one, of course, and let capital U of s be the Laplace transform of u. So we have from this equation the Laplace transform of 0. The Laplace transform of 0 is just 0, right? Because Here's the definition of the Laplace transform. If the function f of t is 0, we're just integrating 0, and the integral of 0 is 0. So that's pretty easy. So the Laplace transform of 0 is 0, but 0 is equal to u prime plus 10u. And the Laplace transform is a linear operator. That means this is L of u prime plus 10 L of u. What is L of u prime? It's S, L of u, u of s, minus u of 0 plus 10 L of u. So this is S plus 10 u of s minus u of 0 plus 7. So when we take the Laplace transform of this differential equation, we get this equation where there's no more derivative. This is just an equation that we can solve for u of s. This says that s plus 10 u of s is minus 7. So u of s is equal to minus 7 over s plus 10. So what this tells us is that the Laplace transform of the solution of the differential equation equals this. So if this is the Laplace transform of u, what is u? We have to find the inverse Laplace transform. So if we look at the table, we see that if you take the function e to the at, its Laplace transform is 1 over s minus a. So this is equal to, we can write this as minus 7 times 1 over s minus 10. So this is, so u of s is the Laplace transform of the function minus 7, let's see, a is minus 10, e to the minus 10t. Notice that when we use the Laplace transform, we're using it preferably when we already have the initial condition, because that's built into the Laplace transform. We're not finding the general solution and then the particular solution that satisfies this initial condition. We're getting the particular solution to this at once. Anyway, this is supposed to be the answer. Let's check. If u of t is minus 7 e to the minus 10t, u prime of t is minus 7 times minus 10 e to the minus 10t, which is minus 10 times u of t. So u prime of t plus 10 u of t is minus 10 u of t plus 10 u of t is 0, and it checks. And also, obviously, u of 0, when you plug in t equals 0, you get minus 7. So we solved the differential equation with this initial condition. Any questions about this?
Professor,
Yeah.
that problem particularly is not involved boundaries in that case because PDE involves boundaries.
So
Mhm.
this is, first of all, this is not a PDE. This is an ODE.
But I mean, when we convert a PDE to the ODE, some PDE have already boundary in place.
That's true.
Right. So right here we got a problem without a boundary variables. So it's another method to use for those type of problems besides this. This is very important because
So,
sometimes get confused between unbound, between bounds,
so
problem
we'll
with.
see examples, but in general, you apply the Laplace transform most easily to initial value problems with no boundary condition. We'll see an example where we do have a boundary condition, but you don't need to have a boundary condition for a partial differential equations problem. You could have an equation, and we've seen, for example, the method of characteristics that we use for first order equations, we use when we have initial conditions, not boundary conditions, what are called Cauchy problems. But let's just do examples and we'll see what happens. And we'll try and make the examples a little bit, maybe more and more complicated. So they work best, the Laplace transform method works best when your ordinary or partial differential equation has constant coefficients. Let's look at a second order equation. Say u double, I'm just going to make this up and hope that we can work out the solution. We'll see. U double prime plus 8 u prime minus 9u equals 0. And let's say we have very simple initial conditions. I don't know, u of 0 equals 0 and u of 1 equals 1. We'll see what happens. So what we will do is take the Laplace transform of this equation, which is the Laplace transform of 0, which is 0. And by linearity, this is the Laplace transform of u double prime plus 8 times the Laplace transform of u prime minus 9 times the Laplace transform of u. What is the Laplace transform of the second derivative? So again, we're going to let L of u, let's just write that as u of s. So this is s squared u of s minus s u of 0 minus u prime of 0 plus 8 times the Laplace transform of u prime, which is s u of s minus s of 0 minus 9 u of s. So this is a quadratic equation in u. Let's see, I have u of s times what? S squared plus 8s minus 9. And here I have minus s times u of 0, that's 0, minus u prime of 0. Here I have minus 8 times s of 0, which is 0. So this is equal to s squared minus 8s minus 9 times u of s minus 1. So u of s is 1 over s squared minus 8s minus 9, which is 1 over, this factors into s minus 9 times s plus 1. And life is easier if I could write this as partial fractions. This is something over s plus 1 and something over s minus 9. Write it the other way. S minus 9, s plus 1. And if I make this 1, if I make this 9 and this 1, I think this, does this work? Let's see. Oops, that's not right. Well, let me just work it out. This is going to be a over s minus 9 plus b over s plus 1. And so that means that a times s plus 1 plus b times s minus 9 equals 1. When s equals 9, I get 10a equals 1. So a is a tenth. When s equals minus 1, I get minus 10b equals 1. So b is minus a tenth. So this is, so u of s is equal to 1/10, 1 over s minus 9 minus 1 over s minus 1. And this looks pretty good. Now, the inverse Laplace transform, let me just write it like this, inverse Laplace transform of 1 over s minus 9, again, look at the table. Is e to the 9t. And the inverse Laplace transform of 1 over s plus 1 is e to the minus t. So if u of s is equal to this, then my function u of t is 1/10 e to the 9t minus e to the minus t. And if we check, let's just check the boundary conditions. U of 0 is 0. U prime of 0 is 1. And you can also check that this satisfies the differential equation. I'm not going to do it right now. But this is the solution, right? So we found it using the Laplace transform. All right. Any questions about this? All right, let's make it a little bit more interesting. This is a homogeneous equation. Suppose we had a non-homogeneous equation. So let it be this. This was u double prime minus 8u prime, sorry, plus 8u prime minus 9u equals t. And suppose we have the same initial conditions. U of 0 is 0, u prime of 0 is 1. So we take the Laplace transform. Let me just write it the other way. The Laplace transform of t is the Laplace transform of u double prime minus 8u prime minus 9u. Now, if we take the function t, the Laplace transform, we actually worked it out in class, I think, on Monday, or you can check in the book, or you can just do it yourself, which is the best thing. The Laplace transform of t is 1 over s squared. Right? So you have to either do it or look in the table. This is equal to Laplace transform of u double prime minus 8 Laplace transform of u minus 9 Laplace transform of u. I already worked that out. Let's see. S squared minus 8s minus 9u minus 1. S squared. Oops, there should have been a plus there. Oh, I just copied this down wrong on the previous page. So let me just go through and make this work properly. So this should be a plus and a minus. So then this factors into s plus 9, s minus 1. See, I should have checked because I would have caught this. This is s plus 9, s minus 1. So this is plus and minus. This would have been minus a tenth. So Laplace transform of s plus 9 is this is minus 9t. And this is minus makes this plus. So this should be plus and minus. This is a minus. Oh, I'm sorry. I should have checked. It was such an easy problem. I didn't bother. But if I had checked, I would have caught it. So So again, we have this non-homogeneous differential equation, ordinary differential equation. U double prime plus 8u prime minus 9u equals t. With this initial condition, take the Laplace transform. Laplace transform of t is 1 over s squared. Laplace transform of this is s squared plus 8s minus 9 times u minus 1. Which means s squared plus 8s minus 9 u of s is 1 plus 1 over s squared. Or 1 plus s squared over s squared. So u of s is equal to 1 plus s squared over s squared times s squared plus 8s minus 9. Or 1 plus s squared times s plus 9, s minus 1. Okay. So are there any questions how I got to this point? Okay. Hopefully I didn't make any mistakes this time. And so I need to find the inverse Laplace transform of that, which is kind of a mess. So what I want to do is write this in partial fractions. This will be equal to sum a over s plus b over s squared plus c over s plus 9 plus d over s minus 1 for some numbers a, b, and c. And I know what are the inverse Laplace transforms of these functions. Right? So u of t, the inverse Laplace transform of 1 over s is 1. So this will be a. The inverse Laplace transform of s squared is t. The inverse Laplace transform of 1 over s plus 9 is e to the minus 9t. The inverse Laplace transform of 1 over s minus 1 is e to the plus t. So this is the solution once I find what a, b, c, and d are. So I always like to find the solution. So let me just do the little bit of algebra required for that. If I put this over a common denominator, I get 1 plus s squared is going to equal as s plus 9 s minus 1 plus b s plus 9 s minus 1 plus c s squared s minus 1 plus d s squared s plus 9. By that s equal 1, I get 2 equals 0, 0, 0. When s is 2, this is 4 times 11 equals 44d. So d is 1 over 22. By that s equal to 9 minus 9, I get 81 plus 1. That's 82 equals, this is 0, this is 0, this is 0. So when s is minus 9, I get 81 times minus 10 minus 810c. So c is equal to this over this, minus 41 over 405. If I let s equal 0, these three are 0, and I get 1 is equal to minus 9b, so b equals minus a ninth. If I pick another value like s equal to minus 1, I get some equation which I can solve, and I know the values of b, c, and d, and I'll find a. And rather than do the algebra now, I won't. But this is the method. Okay. Any questions yet? So let me go to some partial differential equations. And let's try one that's very easy. So we have some function u, which is a function of two variables, x and t. Now I need to explain something. So if I take, so I have two partial derivatives, u sub t, which is the partial of u with respect to t, and u sub x, which is the partial of u with respect to x. So the Laplace transform of u sub x, this is the integral from 0 to infinity, the partial of u with respect to x of x and t, e to the minus st dt. Now, I'm integrating with respect to t, not with respect to x. And if u has continuous partial derivatives, I can interchange integration and differentiation. So this is a theorem in advanced calculus, but we're going to use it. This is the partial with respect to x of the integral from 0 to infinity u of xt e to the minus st dt. This is u of s, so this is the partial of the Laplace transform of u with respect to x at x and s. And then it follows that if you take the second derivative of u with respect to x, this is like the derivative, this is like the derivative of the derivative. So let me just do it in 2 steps. This is like the integral from 0 to infinity, partial squared of u with respect to x squared of x and t, e to the minus st dt. This is partial with respect to x of the integral of the partial of u with respect to x, e to the minus st dt. This is the second partial with respect to x of the integral of u of xt, e to the minus st dt. So this is the second partial derivative of u with respect to x. So that's easy. When you're differentiating u with respect to x, you're just differentiating the Laplace transform. It's different if you have the Laplace transform of the partial of u with respect to t. So that's the integral from 0 to infinity, partial of u with respect to t, e to the minus st dt. If we integrate this by parts, if we have partial of u with respect to t and e to the minus st, the antiderivative of this is u, and the derivative of this is minus s, e to the minus st. We get u of xt e to the minus st evaluated from 0 to infinity minus this integral, which is minus s is plus s, integral from 0 to infinity u of xt e to the minus st dt. When t equals 0, we get, so this is s times the Laplace transform of u with respect to t. And when t is 0, this is u of x 0. So it's exactly analogous to the formulas for Laplace transforms of functions of one variable. Right, this is u of xs. Okay. All right, so let's take the following partial differential equation, and I'll pick one with an initial condition and a boundary condition. So suppose we have the following PDE, partial of u with respect to x plus partial of u with respect to t is, well, x. And we want solutions for t greater than 0, x greater than 0. And for t equals 0, the initial condition is, let's say, u of x0 is identically 0 for all x. And the boundary condition, this is like the boundary is at x equals 0, u of 0 t is also equal to 0 for all x. Okay? So this is a boundary condition. This is an initial condition. So let's take the Laplace transform. The Laplace transform of x is the Laplace transform of u, partial of u with respect to x, plus the Laplace transform of the partial of u with respect to t. Now, the Laplace transform of x, this is the integral from 0 to infinity, x e to the minus st dt. We're integrating with respect to t. This is x, integral from 0 to infinity, e to the minus st dt. This is just x times the Laplace transform of 1. And we know the Laplace transform of 1 is 1 over s. So the Laplace transform of x, right, is x over s. So x over s is the Laplace transform of x. The Laplace transform of u sub x is equal to what? Well, it's the derivative of u with respect to x of xs, that partial derivative. The Laplace transform of u with respect to t is s times u of xs minus the initial condition, little u of x0, which is equal to 0. So now what we have is a ordinary differential equation where the unknown function is u, and we're differentiating with respect to x. This says that u sub x, or du dx, if you like, plus s u equals x over s. So we have to solve this ODE. Well, suppose we had the differential equation dy dx plus sy equals x over s. Well, take a minute and solve that equation. Right? We've reduced the partial differential equation to an ordinary differential equation, but that's only useful if we can then solve the ordinary differential equation. But this is a pretty simple equation. All right. For any fixed s, s is a constant. This is just a linear first order differential equation with constant coefficients, non-homogeneous. We know how to solve that. What do we do? Can someone tell me?
By integrating factor method,
Yeah, so what's the integrating factor?
S.
Well, if we multiply, here, let's take this in the form of this equation, by e to the sx dy dx plus s e to the sx dy dx, of course, that's equal to e to the sxy prime equals x e to the sx over s, right? This is the integrating factor. Let's see. So that's the integrating factor. Spend a minute and see if you can solve this problem, right? First of all, solve the ordinary differential equation problem. That will immediately give you a solution to the PDE problem, right? So take a second and do that. Let's see. Any luck? So let's multiply, let me just do it on this one. E to the sx du dx plus s e to the sx u equals e to the sx times x over s. And of course, this is equal to just e to the sxu prime. So e to the sxu is the integral of x e to the sx dx over s. Yeah. plus a constant. Constant means function of s. Let's see. What is this integral equal to? So we have the integral of x e to the sx dx. So if we're going to use integration by parts, x e to the sx, 1 over s e to the sx. This equals x over s e to the sx minus the integral of 1 over s e to the sx dx. That's equal to x over s e to the sx minus, and when you integrate e to the sx, you get another 1 over, you get 1 over s squared e to the sx. So let me just write this over here so I have some more room. I have e to the sx times my Laplace transform is 1 over s, the integral of x e to the sx dx plus a constant. This is 1 over s. What is this integral equal to? X over s minus 1 over s squared e to the sx plus constant. So if I multiply through, or I divide by e to the sx, I get u of xs. This is canceled. I get x over s squared minus 1 over s cubed plus c e to the minus sx. Right? Any questions about this? Let's see. What is u of 0 s? This is 0. I get minus 1 over s cubed plus c. U of 0 s, this is the Laplace transform of u of 0t. U of 0t is 0. So this is 0. So c is equal to 1 over s cubed. So we get u of xs is x over c squared minus x over s squared minus 1 over s cubed plus e to the minus sx over s cubed. And this is the Laplace transform of u. So we have to find u by the inverse Laplace transform, right? Whose function, what function is equal to x over s squared minus 1 over s cubed and so forth? Well, let's turn to the table. Make a little. The table says that the Laplace transform of t to the n is equal to n factorial over t to the n plus 1. Sorry, over s to the n plus 1. So when you have 1 over s cubed, that's n equal to Laplace transform of t squared is 2 over s cubed. So for 1 over s cubed, this is minus a half t squared. X squared, the Laplace transform of t, is 1 over s squared. So this is x, the inverse Laplace transform of 1 over s squared is t. And the only interesting thing is e to the minus sx over s cubed. So what is that? So we can find that from the table, but we have to do a tiny, 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 tiny bit of work. So if you remember the Heavicide function H, the table says H of t minus a times some function f of t minus a. This has the Laplace transform e to the minus as times the Laplace transform of f of t plus a. Now here, what we have is e to the minus, well, I'm going to use a separate piece of paper for this and then come back. So what we have over here is e to the minus sx over s cubed. So this is of the form. So if you have h of t minus a, this is the Heavicide function, times any function f evaluated at t minus a, the Laplace transform of that is capital F of s e to the minus as, where f of s is the Laplace transform of f of t. Now over here we have what? We have e to the minus sx. So this is like e to the minus, let's say xs. So the x is like the a. So a is equal to x. And f of s is 1 over s cubed. So this is f of s e to the minus as if a is equal to x and f of s is 1 over s cubed. Now, if f of s is 1 over s cubed, the Laplace transform of t squared is 2t over s cubed. So this means that f of t is a half t squared. And f of t minus a is 1/2 a is equal to x, t minus x squared. That's what this is. So the inverse Laplace transform of e to the minus sx over s cubed is the Heavicide function evaluated at t minus a is equal to x, t minus x, times 1/2 t minus x squared. So what that tells us is, for the partial differential equation we started with, u sub x plus u sub t equals x, with the initial conditions, u of x0 equals 0, u of t0 equals 0, for x and t positive, the solution u of xt is equal to xt minus t squared over 2 plus h of t minus x, t minus x squared over 2. Let's see if we can, if this checks. So u of, first, let's check the boundary conditions first. U of x0, when t is 0, we get 0 minus 0 plus h of 0 minus x, x squared over 2. But h of 0 minus x, this is, remember, the Heavicide function, h of t looks like this. It's the step function. So if x is negative, that's 0. U of 0t, when x is 0, we get 0 minus 2 squared t squared over 2 plus, when x is 0, h of t, t squared over 2. But t is positive, greater than or equal to 0. This is 1. So this is minus t squared over 2 plus t squared over 2. That's equal to 0. But what about the differential equation? So this divided into two cases. In the first case, where t is greater than or equal to x. In that case, u of xt is equal to xt minus t squared over 2. T is greater than or equal to x. This is 1. I get t minus x squared over 2. So if I take the partial of u with respect to x, that's equal to t. Differentiate this with respect to x, I get 2 t minus x, the 2's cancel, times minus 1, x minus t, that's equal to x. The partial of u with respect to t is equal to x minus 1/2. Differentiate this with respect to t, I get t minus x over 2. Let's see, is that right? If I differentiate this with respect to t, I get x minus t plus 2 times t minus x over 2, which is t minus x. Let's see. So let's look at the easier case maybe. When t is less than x, this is negative, so this is 0. So this is u of xt is just xt minus t squared over 2. So the partial of u with respect to x is t. Partial of u with respect to t is equal to x minus t. So ux plus ut is t plus x minus t is x, and that checks. So for t less than x, this is fine. And suppose t is greater than or equal to x. So in that case, u of xt is xt minus t squared over 2 plus t minus x squared over 2. If I differentiate with respect to x, I get t 0 plus x minus t, which is x. If I differentiate with respect to t, I get x if I differentiate with respect to t, I get x minus t plus 2 t minus x over 2, which is x minus t plus t minus x is 0. So this plus this is x, and that also checks. So it works. So we actually got this function. It's very interesting. It's a discontinuous function, has this discontinuity. There's a jump when t is equal to x. But that's the solution. That's the solution.
Professor, when we have a continuous function, this special heavy function is continuous, even though it's cut off at some point, because
So in order for the Laplace transform to exist, the function has to be piecewise continuous. It can have jumps. It's piecewise continuous. And in this case, our solution is piecewise continuous, but it does have a jump. Sorry, but maybe I don't understand your question. What is the question again, please?
because this function, the heavy function, is a special case. Jump means it's continuous, it's really continuous function because those PDE require to be continuous.
So,
And right.
so a lot of PDEs that come up in practice involve functions that are not continuous. They have jump discontinuities. This Heavicide function is continuous for x less than 0, is continuous for t less than 0, is continuous for t greater than 0, but there's this jump discontinuity at t equals 0. But that's okay. You can integrate a function with jump discontinuities without any problem. Okay. Well, let me try one more problem. I won't have time to finish it, but at least I will start it, and we'll see how it goes. So, let's see, 8. 12. So this was 13. So this is 14. So this is a non-homogeneous equation. Partial u with respect to x plus partial u with respect to t plus u equals 0. And we want to solve it for x and t both greater than 0. So we have an initial condition, which is u of x0 is sine x for all x. And we have a boundary condition at the left-hand boundary when x is equal to 0, u of 0t is always equal to 0. So this is the boundary condition. This is the initial condition. So take the Laplace transform. We get 0, which is the Laplace transform of 0, is equal to the Laplace transform of the partial of u with respect to x, plus the Laplace transform of the partial of u with respect to t, plus the Laplace transform of u. The Laplace transform of the derivative of u with respect to x is, you take the Laplace transform of u and just differentiate with respect to x. When we differentiate u with respect to t and then take that Laplace transform, we get s u of xs minus what this is equal to, the initial condition when t is equal to 0, u of x0 plus u of xs. So this is equal to u sub x of xs. I have this and this, s plus 1 u of xs minus u of x0, which is sine of x. So we have a first order differential equation in x, u sub x of xs plus s plus 1 u of xs equals sine of x. So this is a non-homogeneous equation. And the integrating factor is e to the integral of s plus 1 ds, which is e to the s plus 1 squared dx, that's e to the s plus 1x. So when I multiply through by this, I get on the right-hand side, e to the s plus 1 times x times the sine of x equals the derivative with respect to x of e to the s plus 1x u of sx. So if I integrate, I get e to the s plus 1x u of xs equals the integral of e to the s plus 1 x sine x dx plus a constant. And if I divide through by this, I get e to the minus s plus 1x, e to the minus s plus 1x. And I do the integral, and I work out the initial conditions and see what happens. So it's a little bit of work to clean up from here, but this integral can be done by parts, and you can find the initial conditions. So what we have here is, this is the Laplace transform of u. And so we have to figure out what this is and then work out the inverse Laplace transform. Okay. So maybe I'll finish this on Friday and stop right now. Are there questions about this? I mean, there's a lot of technique here to learn. I mean, there are 3 or 4 fundamental ways of solving partial differential equations. There is separation of variables. I'm going to go back to that. For certain first order equations, there is the method of characteristics that we've talked about. I'm going to talk about some more. And there is the Laplace transform, which is very used a lot. There's also another transform called the Fourier transform, which I will probably not talk about because that involves complex variables, and knowing complex variables is not a prerequisite for this course. Okay, remember, we are back Wednesday. Sorry, not Wednesday is today. We're back Friday at 11 o'clock. So if there are no more questions, we are done for this Veterans Day. Yes, sir.
Yes, by Friday, I have to work, so you will take attendance because I cannot able to
I'm
go
sorry,
online.
what?
I cannot able to go online because I have to work on Friday.
Right. So I will probably set up another another kind of makeup time. Maybe what you should do is email me various times when you can be online. And I can try, and everyone in fact should do that. And I can try to set up another class at a different time.
Also, if you don't want to take attendance on Friday, I can see through YouTube.
No, it does, yeah, of course, but it doesn't matter because I don't take attendance very much. I do it once in a while, but this far into the semester, I don't usually take attendance. It certainly doesn't count for anything.
Okay, because I can see your video through YouTube, so